from the current slide. Okay. Now let's go over the other minor things. It's just some minor adjustments to my office hours. And I want to get this on here in case people aren't here, they'll hear it too. Today my office hours should be as normal. I may have earlier in the week told you that I was going to have to go to the Birmingham campus today to do paperwork for a vehicle for a field trip tomorrow. Fortunately, my class yesterday, we didn't have a lab, and so we finished and had usually 2 hours that I'm in lab. I wasn't, okay? So I was able to take advantage of that time to go to the Birmingham campus, take care of the paperwork. And so I won't have to do that today. So my office hours today will stand 3:15 to 5:15. However, I've already had a couple people say they're coming by or at least one, coming by for some tutoring. But hopefully that won't be too long. But even if I'm tutoring, if you have questions, I can deal with those. So that's the one issue. Secondly, I'll probably be here after 5:15 because that first mini-term class is ending tomorrow, and they turned in. I gave a test yesterday morning, and except for the 2 tests y'all just came in, still got those to grade, and yours. And then the folks in the first mini-term class turned in that much work yesterday. Actually, I got some of it graded already. So I need to have all this graded before class tomorrow because I want to return things to them. But I'll probably be here well past 5:15, especially with someone coming in for tutoring. If you need anything, come on by. I'll be here. I have no pressure to get home anytime early tonight, so no sweat there. Now, one other thing, I think we've discussed it in this class, is that the CAP exam is given sometime later in the term. I believe that's sometime in April. Is that right? Yeah, there's a few days that's given, isn't it? Yeah, on both campuses, so you got some flexibility there. Please take it and do the best you can if you're graduating this term.
What kind of math, it's just like a general math?
I've maybe sometime long distant past, I've seen the questions or sample questions. I have never seen the actual exam, but I don't think it gets any into calculus. I think it's probably algebra, and I don't know if there's any probability of statistics, maybe a little bit, but I don't think actually any calculus. So you should do quite well, okay? There's what?
There is no way to practice that exam? Like we just go sit down and take it?
Yeah, that's it. Oh, practice. Is that okay? I wouldn't be at all surprised if there's not a way. Follow up on the emails they sent about contact people or other things like that. And if you can't, okay, I'd say follow up in several ways. If you can Google the test itself to see if you might find sample questions that way, and then if not, then locate people. If you can't find anyone, Dr. Renee Herndon on this campus would be the one I would send someone to, and if there's anything, she should know about it, and if not, she should know who should know about it. So if you can't get it by Googling the test itself or the resource or whoever produces the test, then try it through Dr. Herndon or some of the others like that. There almost always are some practice questions somewhere. Yeah. So you can just see the type of thing. Okay, good deal. Any other questions? All right. We left off last time in Chapter 12, Section 12.2. We had just been talking about the equation of a line in point direction form. It sounds a lot like slope-intercept form, doesn't it? Or point slope form. Yeah, point slope form. That sounds just like a point slope form. So I think we start then today at example 4. This is the figure. I can't remember if we talked about this figure. I think we did last time. So let's do example 4. Find the vector parameterization and parametric equations for the line through the point. Ooh, let me get my pen. It won't pick up. There it goes. Through the point P0. And this point is 3, -1, 4. Now we're in 3 dimensions, remember? Okay. So we're going through that point with a direction vector, in other words, a vector in the same direction of V, which is 217. Okay? So, kind of like the point slope formula, except we can't really talk about slopes in 3 dimensions. Well, not yet anyway. There will be a way later. So we want a vector parameterization and the parametric equation. So the vector parameterization is in this form. R as a function of t, or any other single variable you want that to be. Okay? And what you would do with that is do the point, and you'll see this, if we were on the previous slide, you'd see exactly where this is coming from. That would be the point, or the vector going to the point P0. And they call that the vector R0. Okay? Plus t times the vector V. Okay? So, basically all you do is do this point as if it's a vector, 3, -1, 4, plus, and then use the components of this times t. This will be a vector 2t, t, 7t. Okay? Okay. I don't know if this is fair to do or not, but they call this the direction vector. That's the point. So this is almost like a point, because you use those same coordinates here and make them your components of the vector there, plus, rather than slope, direction vector times your variable. Okay, it almost is slope-intercept form. It's not an intercept. It's a point form. So it's kind of a mix between point slope, but it's a lot more like a slope-intercept. Okay, but it's not an intercept. So basically, this vector would then be, you tell me. Say again, 2t. I'm sorry. Plus 3. Add components. Component by component. I'm sorry. See, this doesn't have a t. That one does. 2t plus 3, comma. T minus 1, comma. 7t plus 4. There's the, what do they call it? Vector parameterization of the line in question. And then it asks for, secondly, what is the parametric equations? And those would be your x equal that's your x component. 2t plus 3, y is equal to t minus 1, and z is equal to 7t plus 4. Okay? Now, hopefully it's very obvious to you that this point is on that line. Because you do t equals 0, you get 3 minus 1, 4. 3 minus 1, 4. Yeah, that's there. And it's in the direction of this vector. In other words, it's a multiple of that vector, okay? In a sense, 2t plus t, yeah, plus 7t, okay? So that is in that direction, okay? These are sort of like, this tells you which way it points, okay? So these are those coordinates that you get right off of there, okay? Let's see what they got. R of t is equal to 3 plus 2t. They like to write that first. Negative 1 plus t, they like to write that first. 4 plus 7t. No problem. And then the parametric equations are 3 plus 2t, negative 1 plus t, 4 plus 7t. Okay. Exactly that. Okay. Now, let's move on to example 5. So let's clear this. Any questions on this before we move on? Okay. Example 5. Parametric equations of a line through 2 points.
So, for the example, so basically we have to find the x, y, and z, right?
If it asks for the parametric equations, those were the parametric equations. If you look at the question, it said, find a vector parameterization, that was the R of t, and the parametric equations, that was the x, y, and z of t. X, y, and z. Yeah. That's what those words mean. If you look at the figure, the little blue box right above that example, vector parameterization, R of t, parametric equations, x, y, and z. Right. Okay. Let's move on to example 5. Okay, last time we were given a point and a direction vector. That's sort of like point slope. This time we're given, you're to find parametric equations through a line through 2 points. So this is your 2-point formula. Just like find the equation based on 2 points, and you can do that. So what do we need to do here? Well, here, let's find the parametric equations through the points. P is 1, 0, 2. These are points now, so you put parentheses. And Q is another point in 3 space, 2, 5, negative 1. Okay. Now, you want it through those 2 points. What would be your suggestion of how to begin? Give me some ideas. How is this different from the last one? The last one, they gave you a point within a direction vector, right? So what are we missing here? A vector, a direction vector. Now, what if I had said, oh yeah, why not? Let's do it. What are you thinking? Okay, say that again now. Right, Q as your, yeah. Okay, and what would they be? What do you want to name that back to? You can name it anything you want to except Emmanuel. I don't like that name. No. Second? Omega. Oh, wow, look at that. You want capital or lowercase? Huh? Lowercase. So let vector omega be, boy, he sounds like an angular frequency here. Never mind. Go ahead. What would this one be? 2 minus 1? That would be 1. I can do that. 5. I can do that. negative 3. Is that what you said? Okay. There's a vector. Now what? We want the, it says find the parametric equations for the line. Easiest way for me to do parametric equations is actually write down the vector, r of t. And that would be what? Good question. Which would you like to use? It doesn't matter. P. Okay, let's use P. So that would be 102 plus T times 1, 5, negative 3. So that would be 1 plus T, comma, 5T, comma, 2 minus 3T, close bracket.
What did you say T was? Just a variable?
Huh?
T is just a variable?
I can't hear you. Oh, T, or you can use anything other than something you've already used.
But it's a variable?
Yeah, it's a parameter.
A parameter.
That's your parameter. And that's what they call it, parametric equation. Yeah. Whatever you want to use for that. It could be S, it could be R. No, I wouldn't use R because we got R here. I wouldn't use omega because you already chose that. But if you hadn't chosen that, you could use omega. I probably wouldn't use little p or little q, just that'd be a little confusing too. But A, B, tau, I mean, you get to choose anything you want to, except something that would confuse the issue. They quite often use T. So what they weren't really interested in that, they're interested in your parametric equations, and what would they be? One plus T, 5T. Okay. Now, certainly if you had used the other point, they would be different parametric equations, but they should be equivalent. Now, what I'm interested in is to make sure both of those points are on this vector. And it's really obvious when t is equal to 0, you get 1, 0, 2. Yeah, that one's there. But how do I get point Q on there? Well, obviously t would have to be 1 then. 1 plus 1 is 2. 5 times 1 is, and 2 minus 3 times 1. Yeah, that's minus 1. So both of them are on there. It wouldn't really matter. So with that in mind, if we had chosen the other one, okay, then these would be different parametric equations, but they should yield the same result. Okay, let's see which ones the book used. Thus, the parametric equations are 1 plus t. Oh, they did the same thing we did. Not very exciting, is it? All right, here's Marcus. 3 out of 4 here. Oh, and here's the other thing. I should have mentioned this earlier, but I just remembered it now. I wish our other student would be here so she could hear it as well, but hopefully she'll be listening on this. This week ends the first mini-term. Next week begins the second mini-term. I mean, sometime over the weekend must be midterm, okay? Usually the week after midterm, I believe it's on the campus calendar this way, the academic calendar, that there is they have it written there, midterm progress reports due. Now, sometimes they ask for them and sometimes they forget. So I can't guarantee what they're going to do this time. They may remember or they may forget. But if they do remember and we have to submit them, I have to submit the names of everyone who has a D or an F at midterm. And I think that at least 2 of you have turned in a paper, and I believe now turned in a test too, right? So therefore, 2 of you are covered, but the other 2 are not. So I really encourage you to try to get either your paper or your test or both done either today, tomorrow, or Friday, or over the weekend, so you can get them in early. Get them in the week, so I can put a grade on there, so I don't have to report you as not passing at midterm. So I should have said that in my last class. I think I forgot. I can't remember if I said it or not. No, I don't think I did, because no one was here at the beginning of class, so I forgot to say it. Okay, now here's the key. Yeah. Oh, look at this. I say it and he turns it in. That's pretty rapid response. Okay. Generally, when we list our parametric equations, I haven't been doing this, but really I should. You should always follow this by the, I guess you would call it the domain of t. Where does t vary? And there's nothing to keep this from being all real numbers. Okay? Now, they do make an interesting point, though. No, I'm sorry. No, they don't make the point I was thinking they would. Okay? If you had done the other, it still, I think, would be negative infinity to positive infinity. But the equations would have looked a little differently. And let me just rapidly do one in my head. Well, I don't do anything rapidly. What if this had been a 2, 5, -1 there? Okay. And you've done the same thing. Then you would have 2 plus t, 5, 5 plus 5t, -3, -1 minus 3t. And then to get them to work, you just put in t equal -1, and you would have gotten these here. Yeah, that would work, I think. Okay, so the parametric equations may have changed, but they would plot the same points. Okay, I think. Yeah, they don't go into that, so it really doesn't matter. A lot of times you'll see on questions like this, a variety of answers of equations will work. They didn't say that, but it does. Now, the other thing, and this one then, to complete this, we would have said negative infinity less than t less than positive infinity. Okay. Now, if you had just this, now that would have been fine. A number here, like 0 less than or equal to t less than positive infinity, then that would have been some line, a rate, starting when t is equal to 0 and terminating. It doesn't terminate. Okay, it goes forever. Or this, and you put a number here, 0 or 17 or whatever, -3. I don't care what you put there. That would have been a ray going in the opposite direction. Okay, on that same line. If you had put a finite point here and here, like 0 and 17, that would then give you a line segment, not a ray, not a line, but a segment that begins at this end and ends at that end. So they make a point of that, but that's, I was hoping they were going to say something more than that, but they didn't. Okay, so the parameterization of a line, L is not unique. Hey, they finally said it. I was trying to find that. There it is. We are free to choose any point P0 on L, and we may replace the direction vector V by any non-zero scalar multiple lambda v. However, two lines in R3 coincide if they are parallel and pass through a common point, so we may always check whether the two parameterizations describe the same line. So let's do example 6. I knew it had to be in here somewhere. I just hadn't read far enough down. Here's example 6. Show that R1 of t, which is, it is a vector, so I need vector symbols here. Okay. 1, 1, 0 plus t times negative 2, 1, 3 and R2 is also of t. It doesn't matter. You could have changed variables if you wanted to. And this will be negative 3, 3, 6 plus t. That's a t to it. This doesn't look very t-ish. Okay. 4, negative 2, negative 6. Okay. Show that they parameterize the same line. Okay. They parameterize the same line. Okay. I'm going to try to clean up a little bit of that mess. Okay. Now, how would you go about doing that? And there may be several ways to do it. I can think of one right off the top. Okay. Remember, that basically represents a point on that line, right? And that point on the line we know because when t is 0, it has to be on the line, right? So that point has to be on the line. So the first test I would do is see if this point is on this line. Okay? And it looks like to me it would be true if t was equal to 1. Because if that t is 1, this would be 4 minus 3, that would be 1. 3 minus 2, that would be 1. And 6 plus a negative 6, that would be 0. So sure enough, this point is on that line. Okay. Does that guarantee this point is on that line? May not. So let's do the same thing here. Is this point also on that line? If it is, they are the same lines. If you got two different points and two lines run through that same point, the same 2 points, they're the same line. You can't have 2 points in space anywhere and have 2 lines going through those two and they not be the same line. So let's see if we can go the other way. Is this point on that line? Well, it looks like to me again. Say again? 2. That looks like that might work. Because then this would be negative 4 plus 1 is negative 3. 2 plus 1 is 3. And 6 plus 0 is 6. Yes. So that to me is the easy way to confirm that these two are the same line. Let's see if the book has come up with something more esoteric than that. Yeah, the other way to do it is what they did. They actually came up with a direct. Oh, okay. I'm sorry. I didn't even look at this. These two are direction vectors, right? And just looking at those, you can see this one's a multiple of that. Multiply this by negative 2. Yep, you get this right. So anytime a vector is a multiple of another vector, they're in the same line. Okay, they're not going the same direction maybe because of the minus sign. And one of them's half the length of the other, but still they plot the same thing. So that, I guess, is even easier. Look at the direction vector, see if they're multiples of each other. Okay. They trumped me there, didn't they? Okay. All right. Oh, no. Okay. All that showed is that they're parallel. Sorry. Those two lines could have been parallel, but not through the same points. Then we must check they have a point in common. So if they're multiples of each other and have either point in common, they have the same line. Or if they have both points in common, they have the same line. So there's multiple ways you could do it. Okay. All right. Let's go on to example 7. Any questions on that before we proceed? Intersection of two lines. Determine whether the following two lines intersect. Okay, were these the same lines that I just erased? No, they're not the same line. First one looks similar, but it's not. Okay, here's the two lines. R1 is 101 plus T times 335, and R2 is 361 plus T times 4 negative 27. Okay. Determine whether they intersect. All right. Now, what would be an approach that you might try here? I'm not asking you for if it's the very best approach, but what would be an approach you might try? Usually in plane algebra, if you're staying within a plane, you have two equations, two unknowns. You try to solve them to see if there's some point in common. This only has one unknown, t. So that doesn't, at first, on the surface, look like that might be helpful for you at all. So, what might we do? And I was about to say this earlier. I really don't like using the same parameter, okay, for two different lines, because that almost indicates they have the same values at the same positions, and they don't. So really how they go about solving the problem is saying, is there some parameter you can put in that makes these two lines equal, these two things equal? And if there is, then that would be the point in common. But if you use one variable, it's saying, no, when t is equal to 0, obviously that point is 101, this is 361. They aren't the same. But are there two values for those that you can do? And they use T1 and T2. And that's fine. That's perfectly fine. I would rather use S and T, but T1 and T2 is fine. So in other words, here's a line. 1 plus 3T1, comma, 3T1, comma, 1 plus 5T1. Okay? Here's another one. 3 plus 4T2, comma, 6 minus 2t2, comma, 1 plus 7t2. Okay. Are there any places where those two are going to be the same? Okay. Well, now we have two variables and three equations. Okay. And frankly, you can use any one of them you want to. Okay. For these to be the same line, have a point in common. Just a point, not the same line. These two would have to be the same. These two would have to be the same. And those two have to be the same at that one point. Okay? So, why don't we do that? This is 1 plus 3t is equal to 3 plus 4t. This is t. Wait. 1 plus 3t1 is equal to 3 plus 4t2. And this equation is 3t1 is equal to 6 minus 2t2. Not going to worry about the third one yet. Let's just see what we can do here. Let's rewrite this as 3t1 minus 4t2 is equal to 2. See what I did? Kept this on this side, subtracted this on this side, and subtracted this from that side. Got it? Okay. Second equation, 3t1 plus 2t2 is equal to 6. That 6 is already over there. Okay? Buy it? Agreed? Okay. What if we subtract this equation from that one? So make this a minus, 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 and add them. These go away, and this gives you negative 6t2 is equal to negative 4, right? That means t2 would have to be equal to 2/3, right? Okay. Now plug that back into either one of these two. I think the second one would be easier, and that would be 3t1 is equal to 6 minus 4/3, right? Now that's sort of ugly, so let's multiply everything by 3. That gives you 9t1 is equal to 18 minus 4, right? Okay, so 9t1 is equal to 14. t1 is equal to 14 ninths. Oh, what a lovely problem, right? Now, what are we going to do with that? We know it'll work for those first two coordinates. Let's see if it works for the third one. What is making all the noise? Is it just the windows? Or is something doing some major scraping down here? If it's doing some major scraping, we might need to tell someone. Anything there to scrape, that must have just been the windows. Yeah, those are pretty tight windows, aren't they? Yeah. So I think the storms they were calling for are coming. My mother-in-law, my parents-in-law spent the night with us last night. She had some varicose vein stuff done yesterday on one leg, and today she was going to take the bandage off that. They were going to put a stocking on it, and then they're going to do the second leg, and then they're going to drive back to Huntsville. And I told them before I left the house, look, if you need to stay here until the bad weather passes, then drive, because it's supposed to be worse further north than it is here. And I hope they stayed. I hope they didn't get on the road in this mess. So let's do what they suggested here. Let's plug in the value for T1 here. That'd be 1 plus, is that 70 over 9? So that would be 9/9 plus 70/9 would be 79/9. That would be that third value for that value of T. Let's see what it would be here. 1 plus 7 times 2/3. That doesn't seem too good, does it? I'm not liking this at all. That would be 14/3. That would be 3/3 plus 14/3 or 17/3. And I'm pretty sure that 17 times 3 is not 79. So I did something stupidly wrong here. What was it? Got that. Got that. Got that. Oh, I didn't do anything wrong. They don't intersect anywhere, okay? I was thinking, they said intersection of two lines, I just assumed they would intersect. No, they don't, okay? And we just showed it. Where the first two values have the same, the third one does not, so they can't intersect. Wait a minute. I thought that the two equations, okay, I thought two lines had three options, okay? They either intersect at one point, at no points, meaning they're parallel, or at an infinite number of points, meaning they're the same line. Remember, you did that way back. Well, guess what? You're in three space now, okay? So yeah, they either are going to intersect at one point, or just because they don't intersect doesn't mean they're parallel. Here's a line, there's a line. Okay, in three space, they are anything but parallel, but they still don't intersect. So this sure shows they don't intersect. In fact, I would declare it's usually harder to find two lines in three space that do intersect than those that don't. And of course, the same things, they could be parallel and they could be the same line and they would be parallel, but that's not the only two options. Because you're in three space, you could not intersect, and those are called skew lines. They're not parallel, but they don't intersect. And sure enough, that's the case here. Therefore, equation 8 has no solutions, the lines do not intersect. So all you have to do is show that if you could show that all 3 points, all 3 coordinates are the same, yes, then you would have the case where they did. If you can't show that, then hang it up, Jack. They do not intersect. There is no point in space where that would happen. All right, that finishes 12-2. Finally, okay. Let's see. We must have had some more slides here. Oh, that was just showing that equation we just did, I think. Was that this one? Which one was this? Which one was it? It's example 5. Okay. Oh, in the old book. Okay, we don't have this example in the new book, do we? Okay. It's pretty similar to our example 6 in the new book, it looks like. Okay. Oh, actually, no. This is equation 7 from example 6 in the new book. Do you see a little square that says equation 7? Maybe not. But anyway, this is in the new book, example 6. Okay? It's just after we had done something else, I don't know what it was. Oh, that's the second equation in example 6. Okay, wait. In example 6, what I did was show that both points were on the same line, therefore it's the same line. Okay. What they did was compare the vectors, and they're the same, multiples of each other, and then they just needed to show that one of them was on, and this is the equation whereby they did it. Okay. And then this is example 7. Oh, that's example 6 in your book? Yeah, okay, okay. And this is exactly what we did to show they would have to be the same, and that gave us these 3 equations. And then when you plotted them, notice that that's the trouble with a 3-dimensional graph in 2 dimensions. It looks like they cross right there, but they don't. There's distance between the 2. This is going that. The red line somewhere over the blue line. However it is, and they're not crossing. So that was the illustration of that. Okay. This now, I don't see that anywhere in the new text. So this must have been something from the old text. Yeah, I remember when they did something like this, but that's not showing up in the new text, so don't sweat it now. A line through 2 points. Oh, I guess they're giving you actual formula for this, which is fine, okay? And I think I see the reason they cut it out in the new edition. It really is an awkward way to do it. The way we did it was much more reasonable, okay? But if you follow this along, you'll see it works, okay? Now, this is on the summary on page 642. It's just showing right-hand rule again, okay? And then these 2 formulas, which we've had before, and we actually did a couple of variations on those, but they didn't in the book. I did. Okay, and that is the end of the slide set. You want to do the preliminary questions. Okay? Number 1, what is the terminal point of the vector? This vector V is the vector 3, 2, 1, based at the point P, and the point P is the point with coordinates 1, 1, 1. What is the terminal point of that vector when it's based at the point P, 1, 1, 1? Looking for the terminal point. Okay, what is the terminal point of that vector if it's based at 1, 1, 1? Okay, we're looking, okay. What you're doing that. This is the terminal point minus that. So So 3 is what you want to call it, Q. So let's just call it X. Okay. 3 is equal to X minus 1. So what would X be? 4. This would be 3. That would be 2. So 4, 3, 2. Is that your final answer? Okay. This is 12.2, I believe it is, isn't it? Preliminary questions 432. Excellent. Okay. Number 2. What are the components of the vector v equals 3, 2, 1, same v, based at p equal 1, 1, 1. So what are the components? Say again? 3, 2, 1. Those are the components wherever it's based, okay? You're absolutely right. Those are the components, and they better have that in the back. 3, 2, 1. Good for them. All right. Number 3. This was 1. This is 2. But yeah, I didn't write it down, but hopefully you could hear it. Number 3. If v, not that v up there, but some other v, is equal to minus 3w, w also being a vector, of course, then choose the correct answer. That's what's given. Then A, v and w are parallel. True or false? No, it says choose the correct answer. Okay, B, v and w point in the same direction. Okay, yeah. Between those two, which is the correct answer, or both correct answers, or neither correct answers? A definitely has to be parallel, because one's a multiple of each other. Could they also be pointing in the same direction? Why not? The minus sign is what indicates they're parallel, but obviously going in the opposite directions, with v being 3 times longer than w, but going in the opposite direction of w. Okay, so A is the true one. Good, they got it right. Number 4. Which of the following is a direction vector for the line through the point P equal 3, 2, 1. They like that point, don't they? Okay. And Q is the point 1, 1, 1. They sort of like that combination too, don't they? Okay. So which of the following is a vector, a direction vector, for the line through those 2 points? A would be 3, 2, 1. B would be 1, 1, 1. And C would be 2, 1, 0. Which of those could be, could be, which of the following is a direction vector for the line through those 2 points? C, definitely, because you can do either one of these as the initial, either as the terminal, and 3 minus 1 is 2, 2 minus 1 is 1, 1 minus 1 is 0. That couldn't be, because that would be a vector pointing toward this point. This would be a vector pointing toward that point, and neither one of those would be the vector between the 2 points. That would be it. So we're convinced that's correct. Hopefully they got it right. If I look through the right thing, C is correct. Good for them. Okay. Number 5. How many different direction vectors does a line have? How many different direction vectors does a line have? Why 3? Any reason? 2. Opposite directions? Yeah. That certainly makes sense. Infinite. I would say infinite because they have infinite number of magnitudes. Then double that for direct. No, I'm just kidding. Okay. So it should be, what do they have here? Infinitely many direction vectors, yeah. Because they can have any length whatsoever in either of 2 directions whatsoever. Number 6, true or false? If V is a direction vector for the line L, then minus V is also a direction vector for L. True or false? True or false? If V is a direction vector for the line L, then minus V is also a direction vector for line L. What you think? Yay or nay? Nay? Well, basically what we just said in the last one, any multiple of a direction vector is also a direction vector. That multiple can be plus or minus multiple, but any. This is minus 1 times the other. So yeah, seems like to me that would be true. Yes, it is. Because the other one said you could have opposite direction. This is opposite direction, all right? That's the only difference. Okay? Any question or dispute about that? All right. Homework exercises here do either 1 or 3 or both, either 5 or 7 or both, either 9 or 11 or both. Do 13. Do either 15 or 17 or both. Any of the odds 19 to 23. Either 25 or 27 or both. Either 29 or 31 or both. Any of the odds 33 to 39. Either 41 or 43 or both. Any of the odds 45 through 59. Should be able to do any of those. And I would do more than just a token 1 or 2. Do a few of those that are different from each other. All right. Any questions on that? Okay. Let's now, get out of this and into 12.3. I think I'm taking longer than I intended to take on these. But it seems like it's sort of newish material to all of you, so I don't mind doing it. If I can get this to come up fast. All right, let's go from current slide. All right. This section is talking about the major issue is the one right before us here. It's the concept of the dot product. Okay? Now, if my memory's right, and it may not be, it seems like this book does it exactly backwards from how I originally learned the dot product. Maybe not, I don't remember. Okay. The dot product between 2 vectors. Okay. When we're dealing with real numbers, do we talk about dot products? No, dot product and a cross product are the same thing. It's just multiplication, right? With vectors, it's not. These are very different concepts. The dot product of 2 vectors, V, is a type of multiplication by W between 2 vectors. Number 1, it's a scalar. It's not going to be a vector. Later, we'll do a cross product between 2 vectors. Also a type of multiplication, but then you're going to get a vector. So you need to pay close attention what kind of product you're talking about. This is a dot product, and that will result in a scalar number. So how do we do a dot product between two vectors? Now, number one, the vectors have to have the same dimensions, okay? You can't do a two-dimensional vector by a three-dimensional vector, a 3 by 2, or a 7 by 14, or a 7 by negative 12. You can't do any, they have to be the same. But if they are the same dimensions, if they're in the same space, then the dot product is the product of the first coordinate plus the product of the second coordinate plus the product of the third coordinate. That's it. That's the scalar number defined by those products. Okay? The sum of those products. That is the result of a dot product. Why would we ever want to do a dot product? Because they have uses. Okay? For instance, when you get to physics, those who've been in physics, you realize this already. If you're doing the product of a force, which is a vector quantity, times a displacement, which is a vector quantity, you don't just multiply the magnitude of this force by the magnitude of the displacement. That doesn't get it to you. This does. But the product of those two is the work you've done, or the energy expended. Something like that, which is a scalar quantity, not a vector quantity. Okay? So, that is your one way to lead off with that definition. Okay? Here are a theorem that mentions properties of a dot product. Okay? First, they love this zero vector, even though it's not much there. In fact, there's nothing there, okay? It doesn't have a direction, it doesn't have a magnitude, but we have to define it. A zero vector dotted with any vector v is the same as the vector v dotted with a zero vector, and you dot two vectors together, and you're going to get a scalar, and that's going to be zero always. If either one of those vectors is a zero vector, its dot product is a zero. Because zero vectors, v was v1, v2, v3, so to say. Those were the components of it. This one would then be 0, 0, 0. 0 times v1 is 0, 0 times v2 is 0, 0 times v3 is 0. Add them together, you get 0. Okay. So with the zero vector, obviously commutativity works because everything comes out 0. But even if they're not zero vectors, for any two vectors v and w, of course they have to have the same dimensions. But if you dot those two together, it's the same as dotting them in reverse order. Because if this is v1, v2, v3, this is w1, w2, w3, and this is w1, w2, w3, v1, v2, v3. You dot these, it's v1 times w1 plus v2 times w2 plus v2 times w3, v3 times w3. And here you have w1 times v1, w2 times v2, w3 times v3. Add those together. Doesn't matter because those numbers, which the components are numbers, you multiply numbers in any order, you can multiply. So since the numbers are commutative, the dot products are commutative. Okay. Now, pulling out scalars, okay? It's a strange way, I think, of wording it, but it's certainly what you're doing. If you have some lambda times v dotted with w, or if you have v dotted with lambda times w. In both cases, that's lambda times the dot product of v dot w. And the reason is this lambda multiplies every component of v, like v1, v2, v3, by lambda, so that'd be lambda v1, lambda v2, lambda v3, dotted with w, which is w1, 2, 3. That'd be lambda v1 times w1 plus lambda v2 times w2 plus lambda v3 times w3. Same thing you get if you did it this way, v1 dot lambda w1. That's the same as same as if you dotted those two first and then multiply by them. So that's what they mean by pulling out, or seems like it would be better to say factoring out, but they're saying pulling out a scalar. Okay? Distributive law. Be very careful with this, that you don't extend this to any old distributive law. So here's what you got. The dot product of a vector U with the sum of two vectors V and W. Now, of course, to begin with, before you can do a sum, V and W have to have the same dimensions, and before you can dot, they have to have the same dimensions. So all three of these have to have the same dimensions, okay? And if you had this, then this is the same as U dot V plus U dot W. In other words, you can distribute the U dot across the parentheses. Just keep it in front and both. Okay. What if it's the other way? V plus W dot U. Now basically that's just commutivity. This is being commuted with that. Okay? And this is V dot U plus W dot U. Okay? And frankly, those two are the same. U dot V and V dot U are the same from up here. U dot W and W dot U are the same from up here. So the sums would be the same. So everything there is the same. Okay? Relation to the length. Okay? If you think about it, what is the length of vector V? The magnitude of V. It's the square root of V1 squared plus V2 squared plus V3 squared, right? Isn't that what length is? Of a vector would be the square root of the square of each of its components, sum of the squares, okay? But guess what you would get if you multiply V times V itself? V1, V2, V3 times V1, V2, V3, V1 times V1 plus V2 times V2 plus V3 times V3, V1 squared plus V2 squared plus V3 squared. What's that? It's the square of the square root. It's just the sum of those things. So sure enough, there's another way to get the magnitude of a vector. Rather than taking the square roots, dot the vectors, well then you have to take the square root. But you don't have to do the individual components. Just do the dot product, which is pretty easy to do, and take the square root of it. The principal square root, positive square root, if you're talking about magnitude. Any questions? All right, I think this refers to example 1. Let's just see what the picture looks like up close and personal. No, it isn't. Sorry. All right, let's work example 1 here. Verify the distributive law. Yuck. Okay. Verify the distributive law U dot V plus W is equal to, you tell me what it is. U, tell me what that distributive law is. U dot V plus U dot W. Okay? Verify that for these vectors. Vector U is 433. Vector V is 122. And vector W is 3, -25. Okay, that's an ugly looking 5. Okay, that's even uglier. Let's see if we can clean that up. Oops, wrong pen. Okay. Okay, that may be a little better. Okay. Let's do the left-hand side. That would be U is 4, 3, 3, dotted with, can we just add those two vectors together? What would that give us? 4, comma, V plus W. Second, adding V and W together. Those two. 4 is the first component. What's the second component? 0. Third component? 7. Okay, dot those two vectors together, and what do you get? 16 plus 0 plus 21. And that dot product is equal to 37. Okay? Now let's dot these two vectors together. Okay? U dot V. What would that be? U and V. 4 plus 6 plus 6, and that would be 16. Let's dot U and W together. U dot W. That would be 12 minus 6 plus 15. Okay? All right. Sorry, wait. Eyes are stinging so bad it hurts to try to look. So that would be 27 minus 6 is 21. You're absolutely right. And that says if you add these together, what do you get? 37. Okay, we verified it for those three vectors. Does that make sense? All right. Now we move to this slide. Okay? This had nothing to do with example 1. This was figure 1, but except for having 1 in it, has no value. Okay. All right. Does anyone see anything wrong with that figure? Probably what's in your book, but not your books. Okay. What's wrong with that? Yeah, that pi is not pi. Pi is a straight line. That's not pi. Okay. That should be theta. Okay. Now go to right on it. It's going to shrink. So this not pi, but theta. Okay. With that correction made, this is correct. If this is some angle theta, the angle over here is 2 pi minus theta, because 2 pi would be all around here, minus the theta that would subtract off that part, so this would be the angle 2 pi minus theta. Now, by convention, the angle theta between two vectors is chosen such that the angle you're looking for, this is the convention, is the smaller of the two angles. If you got an angle and its supplementary angle, no, that's not even right. So anyway, so dry it hurts to look. So we keep theta between 0 and pi. Okay? Could be equal to 0, could be equal to pi. We don't ever let it get bigger. If we let it get bigger, then we would use the angle down here. Okay? If this theta extended past that, then we would use the angle down here. That's what they're getting at. It's always an angle between 0 and pi. That's what it says. Okay. Now, so as mentioned above, the dot product V dot W is related to the angle. Where did it say that? I guess this is in the side note. I don't even see it there. But anyway, somewhere up here it said it mentioned something about the angle. This, to me, looks like the first place we've said it. But anyway, it's true. It's the dot product is related to the angle theta in between U and V. That angle theta is not uniquely defined because, as we saw in figure 1, both theta and 2 pi minus theta can serve as the angles between V and W. Therefore, furthermore, any multiple of 2 pi added to that, either one of those would be related to that angle. All those angles have the same cosine, so it does not matter which angle. Goodness gracious. Which angle we use in the next theorem. However, we shall adopt the following conventions that will choose the angle between 0 and pi. So here's the next theorem. The angle between two vectors is chosen to satisfy it to be the angle between 0 and pi. All right, here's the dot product and the angle, how they're related. Why did we bring this up anyway? All right. Okay. Let theta be the angle between two non-zero vectors, V and W. Now, there can be any vectors in space, okay? Anywhere in space. Let theta be the angle between them, okay? Then the definition of V dot W, besides the one we just used, V1, W1 plus V2, W2 plus V2, many times you use me to, here's another definition. Magnitude of V times magnitude of W times the cosine of the angle in between those. Okay? Now, rearrange that slightly, divide both sides by the magnitude, and you get the cosine of the angle is the dot product between the two angles divided by the magnitude of those two angles. Okay? The product of the magnitude of those two angles. Okay, and then if you wanted to take it one step further, you could say theta is equal to the arc cosine or inverse cosine of this quantity here. Okay. Now, what does that suggest to you? Suggests to me that this dot product is always less than or equal to the product of the magnitudes. Got to be, because cosine has to be less than or equal to 1, okay? Or between minus 1 and 1. But if we're letting the angle always between 0 and 90, or 0 and pi, then the cosine is positive in the first half of that, negative in the other part. So you can have a negative up here. Okay. The dot product can be negative, by the way. Okay. Okay, this is the Theorem 2, top of page 646. Yeah. Okay. All right. Now, they're going about to prove this. Okay. Now, does this look similar to something else you run across in trig maybe? Remember the law of sines and the law of cosines? Which you reckon this one would be more related to? Law of cosines, right? Do you remember how that worked? No, it's been a while, right? Okay. The law of cosines basically said for any triangle whatsoever, yuck. Okay. any triangle. Okay. It seems like I can't draw a triangle and one of the angles not turn out being close to 90 degrees. Well, let's just imagine it's not. And let's pick any old angle here, theta. Okay? Now, what the law of cosine says, okay, let's name a few things here. So this be A, this be B, this be C. Okay, then this angle theta here will be related to B. You could call it capital B. The angle here could be capital B, and the angle here, capital C. Okay. Now, if indeed, and mine doesn't look like it's far off, but if indeed this were a right angle, which it doesn't have to be, I was trying to draw it so it wasn't, and I still wound up getting it looking like it was. But anyway, if that was a right triangle, we know that a squared plus c squared, a squared plus b squared equals c squared, Pythagorean theorem. But if this is not a right angle, then we still have it true that a squared plus b squared is equal to c squared, with an adjustment, okay? And here's, if that angle wasn't 90 there, let's say, then we would have the a squared plus b squared minus, I believe it's 2ab times the cosine of, I've used the wrong letters. Let's use this angle as the angle C. Cosine C, that's equal to c squared. I believe that's it, okay? If you're not certain, law of cosines, a squared is equal to b squared plus c squared minus 2bc cosine A. Yeah, same deal, okay? Now, and in fact, that's the way they define it. So they say c squared is equal to a squared plus b squared minus 2ab cosine. And they said theta, but I was using angle C. So to get in line with what they're doing, this is the angle theta. Okay. I was calling it angle C. They're calling it angle theta. Okay? Now, oh man. The rest of this theorem is fairly straightforward. I'll let you read through it. I just want to make sure you recall law of cosines and why it was true and stuff like that. But I'll let you finish looking at that. And let's us move on to, let's see. Okay, I don't think I need any more there. Thought I wasn't going to do it anymore, but I guess we are. This is the illustration that's used to prove that theorem or to deal with it. All right, here we have a triangle with lengths A, A, B, C, and the angle theta. Now we're going to represent that same triangle with vectors V, W, and this would have to be V minus W. I don't know if you recall that, but it has to be true, because if you do V minus W, W in the opposite direction here, then that angle between there would be V minus W, and that's exactly the same vector as that. Okay? Now, using law of cosines up there and substituting the values here, you do come up with exactly what we were getting at, and that was the formula. And this is, wow, they've got a lot of this theorem proved here. Okay, and this is basically saying what the law of cosine says. That the magnitude of the opposite side, which on our last slide, that was V minus W, that was also called C. The magnitude of that squared is equal to the magnitude of the first one squared plus the magnitude of the second one squared minus 2 cosine theta times the magnitude of the first times the magnitude of the second. Okay. That's directly from the law of cosines. Sort of indisputable. That's what it is. All right. Now, with that done, we can go to the next one, which is, there's, as usual, there's a lot of little gaps in what's going on here. If you remember what the magnitude square was, that's the dot product of those two vectors. Okay? But if you remember what the dot product is, that's V dot V minus 2 times V dot W plus W dot W. Sorry, having trouble swallowing. This is V dot V is V's magnitude of V squared. This is W, that's W dot W is magnitude of W squared. And then this is minus 2 times V dot W. Okay? Now, are they going to show the final blow here? Okay. And then when we go back up above, we'll see that is indeed 2 times the cosine of V dot W. Okay. Now, what that leads to is this. And basically, I said it a couple slides ago, okay, when they had cosine theta is equal to V dot W over the magnitude of V times the magnitude of W. I said then you can take the inverse or cosine on both sides, and this would be the argument of that. The arc cosine of that would be your angle theta. Okay, and I guess from the sounds, it sounds like we're running out of time. So what we're going to do next is start with example 2. Got just a tad further from than we did last time. Let's see if we got enough done that we can do any homework exercises. It's a fairly short section. I think, for sure you can do any of the odds 1 through 11. But I think you got to stop there, because the rest of them require things about orthogonality, and we haven't gotten there yet. So any of the odds 1 through 11. Good deal. Please, okay, I think all of you have gotten me some input. That one person who's not here, I don't don't think has. So if you do see her in another class or something, share the news, okay? I'd like to have something in next week. Okay, good deal. Now, I'll see you in a few minutes and the others coming in. Have a good weekend, you too.